Hello again and welcome to another lesson in the Designing VMware Infrastructure video training series. In this lesson, we're going to be discussing sizing hosts, clusters, and resource pools. This lesson is the culmination of a series of lessons discussing the translation of a logical design into a physical design. In this lesson, we're first going to take a look back at the logical compute design and review the information that was created and discussed there. From there, we're going to move into sizing our hosts and discussing strategies for how we do that. Then move into creating clusters, scoping our resource pools, putting things together, a quick look at how we need to pull the design together. We've been talking about it in different pieces and parts, although stressing the need to keep a holistic view. We're going to reinforce that here and round out the lesson with an analysis of design impact. Again, stressing the need to understand the relationships and the dependencies between the different portions of the design. Let's get started. If you need a refresher on the information that was included in the logical compute design, I'll refer you to the lesson titled Defining a Logical Compute Design so that you can refresh your memory on what we defined when we defined the logical compute design. What we included there and what we derived from the design factors in creating that logical compute design was first a total CPU capacity, an aggregate CPU capacity, typically expressed in some gigahertz of CPU cycles necessary in order to process or support the processing of the workloads. We also defined an aggregate RAM capacity number, typically some number of gigabytes or perhaps terabytes of RAM. And we also identified our socket to core and target VM to core ratios, which help us have a better understanding of how many VMs and how many hosts are required to support those VMs. What we're going to do now is take the high-level specifications found in the logical compute design and map those onto real solutions and real products. This is part of our ongoing process of taking the logical compute designs that we've defined in various areas of the VMware infrastructure and mapping those onto a physical design that can be implemented. Let's start by discussing how we go about selecting and sizing the hosts, the compute nodes that we're going to use. When it comes to sizing hosts, at this point it's less about total compute capacity because we've already taken care of that in the logical design, and more about how we're going to slice and dice that compute capacity. Recall from the logical compute design lesson that we already arrived at a aggregate CPU capacity number. We already know the total compute capacity number. We already know the total RAM capacity number. And we got that from an assessment of the current environment or an assessment of the applications that we're going to run in here. Now we need to decide in the design how we are going to implement that total aggregate number. And we have two basic strategies we can follow. We can use a scale-up strategy, or we can use a scale-out strategy. A scale-up strategy means fewer hosts, but those hosts are larger in capacity. A scale-out strategy means more hosts, but each host is smaller with regards to total capacity. Now, each of these strategies has its pros and cons, its advantages and its disadvantages, its benefits and its drawbacks. And of course, it's your job as the architect to weigh those pros and cons against the design factors and determine which strategy best satisfies the design factors. Now keep in mind that these strategies both affect other things and are affected by other things. And what I'd like to do now is talk a little more about each of these strategies in a bit more detail. The scale-up strategy, as I mentioned, uses fewer number of servers, but each server has greater capacity. So we're talking more sockets, more cores, more RAM, more expansion slots, more internal disks if you're leveraging internal storage, etc., etc. Now, because of the greater capacity for each of these servers, you're typically going to see more VMs running on each server, which means higher VM to core ratios potentially, and it certainly means more VMs would be affected by an issue with a single host if a single host were to fail, although failures are rare due to redundancy built into the hardware and just the improving quality of hardware. If a failure does occur, more VMs would be affected. Typically in this sort of strategy, we're going to see the use of rack mount servers, and that would typically be larger rack mount servers, not the 1U servers that may be common in some environments. Now, this can provide benefits in power and cooling density, which is something that you're going to want to consider rather than looking at a scale-out strategy, which I'll describe in more detail in just a moment. You may prefer to use a scale-up strategy which would help perhaps in an older data center where satisfying the dense power and cooling requirements for a scale-out strategy may not be possible. It can also provide additional expandability. So if you are implementing a design where perhaps the hosts are configured smaller but with more headroom for additional growth, so the environment can grow without adding hosts but instead grow within each host, then a scale-up strategy may be a better approach because you'll have headroom within each host to add additional RAM, additional sockets, anything of that nature, perhaps additional expansion cards, network cards, or storage connectivity cards if that's what's required. Now let's compare and contrast the scale-up strategy with the scale-out strategy. The scale-out strategy takes an approach where I'm going to use more servers. I'm going to use a greater number of servers, but these servers will generally be a bit smaller in capacity. Now, because these servers are generally a bit smaller in capacity, we would typically see a fewer number of VMs or a smaller number of VMs on each host, and that can result in lower VM to core ratios and would naturally result in fewer VMs being affected by an issue that involves a single host, whether that be a loss of network connectivity or a hardware failure or even an operator-induced failure that caused an outage. Now, typically, this sort of approach is going to involve blade servers or perhaps highly dense rack mount servers. In both of these situations, whether it's blade servers or highly dense rack mount servers, 1U, or perhaps there are some rack mounted options that aren't quite blades but aren't quite typical full width rack mount servers. They're kind of a hybrid of the two. These can help in situations where there are limited physical space. So if you are constrained for rack space, constrained for floor tile space within the data center, and you can address the power and cooling densities that are generated by a large number of servers in a small spot, then this sort of approach might be very beneficial. Depending on the type of compute node solution that you select, you may also reap some manageability benefits. Many blade chassis offer centralized management of some number of the servers, so one point of management to address some grouping of servers, whether that be the chassis or some number of chassis depending on the vendor. So there are some potential manageability benefits that you're going to want to consider there as you look at these two strategies. So how do you choose whether you should go with scale up or scale out? Well, that's going to be driven by your design factors. Although I've mentioned the server form factor, i.e. blade servers versus rack mount servers a little bit, it is naturally intuitive that that will affect your strategy, and vice versa, your strategy will affect your server form factor. While you could do a scale out approach with larger rack mount servers, you typically wouldn't do that because of the increased physical space that is required. Although you could do scale up in some cases with blade servers, you typically wouldn't do that because of the limited expandability. Now, those are broad generalizations, and there are always exceptions to the rule, so keep that in mind. When you consider which strategy you need to take and which form factor you need to choose, you also need to consider a number of other factors. You must consider network connectivity. Can the form factor and the server strategy that you're using address the required network connectivity that you specified in the physical and logical network designs? Storage connectivity. Can your server form factor and the server strategy that you're going to use provide the necessary storage connectivity to your storage solution? Expandability. Do you have enough expandability in your hosts to address future growth? Will you address growth through expanding within a node or by expanding the number of nodes? I discussed briefly already manageability, but how are the various compute nodes managed? Is there any form of centralized management? And kind of wrapping a lot of these previous bullets together, but you'll also want to consider operational aspects. Here's an example. If you are already running virtualized hosts in your environment and you are simply creating a design to expand that existing environment, and you're using rack mount servers in your existing environment, there are operational considerations to switching to blade servers. Or vice versa, if you're already using blade servers and you're considering using rack mount servers, there are operational considerations. Not listed here, but also things you'll want to consider will, of course, be financial constraints, the costs of the various compute nodes, the cost to manage them, the cost to operate them, and any sort of existing experience for your staff. I suppose that could be rolled into operational aspects, but if your staff is already accustomed to operating HP ProLiant servers and then you decide you want to switch to IBM, that could create some operational aspects you'll want to consider, so that's something else to keep in mind as you go about selecting the specific compute nodes that are going to be used to construct the logical compute design and provide that total number of aggregate CPU cycles and total amount of aggregate RAM. Now, once you've selected those pieces, the next step is to decide how we're going to group them, and in a VMware environment, we typically group them using clusters. Just as with the individual compute nodes themselves, we have kind of two basic strategies with clusters as well. We can use a scale-up approach where we have larger clusters, but a fewer number of clusters overall, or we could use a scale-out approach where we have fewer hosts in the clusters, but a larger number of clusters. And these strategies are going to be driven by the design factors, naturally, as design factors drive just about everything in our design. But they'll also be affected by operational considerations, geographical considerations, network connectivity, storage connectivity, all of that. And I'll go into all that in just a moment. You want to consider also that management design may also affect your cluster design. If you've selected in your management layer to use a virtualized out-of-band management approach, then you're going to need a separate cluster, generally speaking, to drive your management components. Now, the two approaches here that I've described, scale-up clusters versus scale-out clusters, just like at the host level, there are advantages and disadvantages, pros and cons, benefits and drawbacks. You're going to want to consider all of these against the design factors and against the other considerations in the design. Let those design factors and those considerations be your guide to determine which approach is best. You may also have design factors that will lead you to say, I'm going to have some hosts that are going to be standalone for certain purposes. And business factors are also going to drive the creation of clusters. Things like application ownership, management of the applications may also lead a cluster design. Now let's look at some other factors that may drive how we go about cluster sizing or sizing our clusters and how we go about determining how many clusters we're going to use. Whether or not we use a scale-up approach or a scale-out approach, basically how large our clusters are going to be, is driven by a number of potential factors. This is not a comprehensive list of factors. There are many, many more, but this should get you thinking along the lines of what could affect your cluster design. First is licensing, and I have an example here of Oracle. Some vendors do not support the idea of clusters or subclusters as being licensing boundaries. In Oracle's example, if you want to run Oracle on a node in the cluster, then you have to license Oracle on all the nodes in the cluster. And so that could constrain the size of your cluster and could also drive you to create a separate cluster that is specifically targeted at running Oracle applications in a larger environment. You'll also want to consider, and what will affect the sizing of your clusters and the creation of the clusters, is how you're handling your shared storage presentation or your SAN zoning. Are all the hosts going to be exposed to the same storage arrays because they are going to need common shared storage for things like vSphere HA and vSphere DRS? So if you have hosts that will not be connected to the same data stores, they can't be part of the same cluster. Your chosen redundancy level, whether you're doing an N+1 or an N+2 or even something greater, will also affect the size of the cluster and the number of clusters you create. CPU architectures will create what are called vMotion boundaries or cluster boundaries. If you have some hosts that are Intel-based and some hosts that are AMD-based, then you're not going to be able to perform live migrations between those hosts, and therefore it doesn't make a lot of sense to have those hosts in the same cluster. Network connectivity is another area that will affect cluster design. You have to have some common networks in order for VMs to be able to move around, and if you can't establish that, then you're going to want to create separate clusters. And the total number of VMs is also a consideration. Not only the total number of ESXi hosts, but also the total number of VMs. There are some constraints, although they are very large, on the total number of VMs that can run within a cluster, so you'll want to keep that in mind. Your cluster configuration is not just about the number of hosts, but it's also about how those clusters are going to be configured. And generally that means we're talking about the configuration of technologies such as vSphere HA, high availability, vSphere DRS, distributed resource scheduling, and EVC enhanced vMotion compatibility. Let's take a quick look at some of that. Now, your design needs to be sure to include any configuration parameters for vSphere HA and DRS. I didn't go into any specific examples here because there are so many and they are so varied that any discussion would naturally just be incomplete. But we're talking about things like our overall vSphere HA configuration, how many failover hosts, what is our tolerance for failover, what is the admission control, all of these sort of things. You want to make sure that you understand the impact of every single one of these parameters on the design. If you set, for example, to enforce admission control, what is the impact of that? If I set a failover level of 2 failover hosts, what is the impact of that? If I use the percentage failover to be able to say I want to support up to 50% failures, what is the impact of that? If I configure DRS in a certain way, what is the impact of that? If I configure DRS to be fully automated or to be manual, what is the impact of that? You have to make sure that you understand the impact of each of these parameters. There are lots of great resources that go into an extreme amount of detail on the configuration of vSphere HA and DRS. And if you aren't familiar with these technologies and aren't familiar with the impact of the various configuration parameters, I would definitely encourage you to have a good look at those before you attempt to move into the VCAP DCD exam. Note that while we can use Enhanced vMotion Compatibility, or EVC, to help with differences in CPU families, we can't overcome the Intel AMD boundary, which is why I listed that earlier as kind of a hard boundary for clusters. We can overcome differences, say, between the Intel and the Halem series, or the Xeon 5500s, and the follow-on 5600s, even though there are differences in the underlying CPU registers. Enhanced vMotion Compatibility can mask those to help with adding new hosts into an older cluster. Keep in mind, though, that EVC should be enabled before you start putting workloads into your cluster. If you have workloads already in the cluster, then you have to coordinate adding EVC carefully, because that requires an outage for VMs. So that's something to keep in mind, not only for the design portion, but also for the implementation of the design, which I'll discuss in another lesson in this course. Resource pools are another key area that we have to talk about when we talk about the logical compute design being translated into a physical design or a final design. Resource pools are, of course, logical constructs that exist at the hypervisor level. It's very important to understand that resource pools are for adjusting resource allocation, not for organizing VMs. So I strongly discourage the use of resource pools as a way of grouping VMs from some purpose. VMware vSphere offers folders in various areas to help with that. Use folder constructs, don't use resource pools for that. How do we go about deciding how we're going to use resource pools and how those resource pools will be configured? That's driven by the design factors, especially any performance-oriented service level agreements, or SLAs. If you have specific applications that have a particular business impact, perhaps they are business critical, perhaps they drive the bottom line of the business. Consider an online retailer. Their web servers and the applications that process online orders are the bread and butter of that design. And if there's anything that impacts the ability for those to respond very, very quickly, then that translates immediately into lost revenue for the organization. So that's an example of where design factors, particularly performance-oriented SLAs, are critical. You'll want to make sure that you understand the behavior of resource pools. And again, if you're not comfortable with how resource pools work, there are a variety of resources, sorry for the pun, available to help you understand that. Keep in mind that you should have a good understanding of resource pools by the time you're moving into looking at this sort of process. This is something we discussed early on in the course in one of the very early lessons about how the role of a vSphere architect is inclusive of the role of a vSphere administrator, and how you have to have some of that administration experience in order to be an effective architect. So when we talk about understanding the behavior of resource pools, you have to make sure that you can answer questions such as how are resources allocated when a VM is placed at the same level as a resource pool, or how are resources allocated when a resource pool is nested inside another resource pool. And to help illustrate and bring home that difference, I want to show you this screenshot taken from the vSphere client. So in this screenshot, it's a look at the resource allocation tab for a cluster, and I have both VMs and resource pools at the same level. And let's assume that there is at least one VM in each of these resource pools. I want to draw your attention to the percent shares column. In the event that this cluster becomes resource constrained, and we're looking at CPU capacity right now, so if I were to become CPU constrained in this cluster, note that the presence of how VMs and resource pools at the same level interact with each other means I could potentially see VMs in the production VMs category taking a significant share of CPU percentage away from all the other VMs. So if your intent was to help balance things out evenly, this particular organization wouldn't do that. So make sure that you understand how resource pools work. When you define resource pools in your design and specify how they're going to be used, make sure that you understand the impact of that on the overall design and how the environment is going to operate once it's up and running. Now, I've tried to stress the need to maintain a holistic view as we've moved throughout the design process. But nevertheless, we've had, just from a nature of organization purposes, we've had to discuss individual design areas. So we've had to discuss storage and networking and security and compute. But by the time we get to this point in the design process, really we are needing to pull all these things together because the hosts are somewhat of a connection point between a lot of different aspects of the design. So while you could potentially, depending on the technologies that are involved, have created a network design that is not terribly affected by or affecting the storage design, and you might have a management layer which is not terribly affected by other aspects, when you plug your compute nodes in there, these are kind of at the center of all that's going on. So your compute nodes are going to have a direct impact. They're going to directly influence and be influenced by the network design. Your compute nodes are going to be directly connected to the storage design and are going to have a direct impact on and be directly impacted by the storage design. Same goes for management, same goes for security, same goes for backup and availability. This point, defining or selecting your compute nodes and putting them in the center of this design, kind of like a puzzle piece that gets inserted and connects all these pieces together, all of the various aspects of design are going to become much more tightly coupled than they have been perhaps in earlier portions of the design process. So now more than ever, it's critical for you as the architect to make sure that you are thinking holistically, that you are taking a broad view across multiple disciplines and understanding that there are relationships and dependencies between these things. And I've reviewed this with you several times, and we're going to do it again here in just a moment. And the very next slide, as a matter of example, we're going to take a look at analyzing for design impact, and again looking at how one area of the design can affect other areas of the design in ways that perhaps we didn't anticipate if we don't really take the time to do that. So let's dive right into that real quick. Looking at analyzing for design impact, I've chosen here to use a mind map once again, and we've used mind maps in a variety of different areas through the course, and we've used other things. We've used tables, we've used lists, we've used what-if scenarios. So we've looked at a lot of different areas, and I'm going to continue to try to provide as great a variety as I possibly can as we move through here. But when we come to the point of physical host selection, we have a lot of different things we have to select here, and this has a very broad impact on a lot of different areas. So if we look, for example, just at the aspect of physical form factor, so before we even get into how much RAM is each server going to have and how many sockets and cores are going to have, if you look just at the idea of physical form factor, that affects how expandable the servers are going to be. Typically, rack mount servers are going to be more expandable than blade servers or highly dense rack mount servers. It's going to affect your network connectivity, your storage connectivity, your financial constraints, your physical constraints like power, cooling, rack space, floor space. All of that are going to be affected by the form factor. The strategy that you're going to use, even your licensing, can be affected by the form factor because your form factor will determine how many sockets and cores, which is directly how you go about licensing VMware vSphere. I won't go through all of these areas because you can review this, and this should be, at this point in the course, fairly intuitive to you. But I did want to reinforce the idea once more that it is important to maintain that holistic view and important to take the time to explore relationships and connections between different areas of the design to ensure that you understand the impact of the various design choices that you're making. All right, now as I wrap up this lesson, let's quickly review what we covered in this discussion on sizing hosts, clusters, and resource pools. We first took a look back at the logical compute design to remind us and refresh our memory about the aggregate numbers that were specified in the logical compute design. From there, we moved into a discussion of how we go about selecting our compute nodes and sizing them to appropriately satisfy the design factors and to minimize the design impact on the rest of the environment. Following that, we discussed creating clusters and discussed some of the factors that will lead us to how many clusters we're going to create and how large those clusters are going to be. We then discussed scoping our resource pools, looking at the factors that are going to drive the creation of resource pools and how many we're going to have and how they're going to be configured. I then reviewed how it's critically important at this time. We began really pulling things together because the compute nodes, the physical compute design, the hosts and the clusters and the resource pools kind of pull all this stuff together, and they both affect other areas and are affected by other areas very, very tightly. And finally, we wrapped out the lesson with an analysis of design impact and tried to reinforce once again the holistic view of the design to understand relationships and dependencies. That's it for this lesson. Thanks for watching.